Hello, I'm Tanya Wang. I'm going to present this work that was done by my undergrad students and myself. So the topic of the work is trends in the simulated airglow temperatures in the MLT region. So the motivation for this work is that the society is very interested about climate change and global warming. So the question is, what causes global warming in the lower hemisphere? And we know that, there are several possible candidates. For example, variations of solar radiations, increase of anthropogenic gas emissions, and also changes in the Earth orbits. So what about the upper hemisphere? How does the upper hemisphere respond to the CO2 concentration increase? Robert and Dixon, they use a one-dimensional global model, predicted a 10K decrease in the mesosphere for a doubling of CO2 and methane. And the same study also predicted that a 30% to 50% of decrease of major gas species and atomic oxygen at 300 kilometers. And it was found that neutral densities derived from the satellite direct measurements show a decreasing trend. However, temperature measurements show rather ambiguous results. And several studies also have indicated that trend results highly depend on trend analysis. In other words, how you analyze the data might have influenced the outcome. So to derive the temperature trend by CO2 inference, natural variability and dynamic inferences need to be quantitatively assessed and identified. The latter inference can be ignored if we use a time scale that's much longer than the time scales of dynamical processes. Airglow is also known very sensitive to the local temperatures and the number density of the species reacting the airglow chemistry. It has been used as a diagnostic tool to infer the state of the atmosphere. So the study aims to answer the following questions. How do airglow temperatures respond to the increase of CO2 gas concentration and to the natural variability like solar cycles and geomagnetic activity over a period of time? And what are the trends in the temperatures in the MLT region? So the approach for this study is we're using a numerical simulation, and it's a modeling approach. We use two models. One is called the MACD model, which includes the green light O2 and ultra-atmospheric band airglow and an output O2 and also green light temperatures. And the other one is OHCD00 model that has the OH airglow chemistry and also OH temperature. So the 00 here indicate the reference model that we use. So both models use the MRL M600 as a reference model to obtain the number density and kinetic temperature. And so the airglow temperatures, they are obtained from the kinetic temperature weighted by airglow intensities. And then instead of using the monthly or daily, we're using the annual average of airglow temperatures, and they are obtained from those two airglow models. F10.7 was used as a proxy for solar cycle variations, and they are taken from NASA's website. The AP index values, they are proxy for geomagnetic activity. They were taken from the World Data Center for Geomagnetism. And the CO2 gas concentration were obtained from no other website. Gas concentrations and temperature changes in response to the increase of CO2 was from a linear scaling of Robert Dixon's numerical model results to the actual CO2 levels. So this tells you the fractional change when there's a change in the CO2. And break it down into the altitude, in altitude, because they respond differently depending on the altitudes. Now, regarding the impact of a reference model on our simulation results, we just need to mention that before we talk about before we discuss our results. So we do have to know that F10.7 AP variations, they have not been carried below 110 and 90 kilometers respectively, where their coefficients became insignificant in the MC90 or MRL00 models. So this definitely will have some impact in our numerical simulation. But we should also point it out that the MC90 and MRL, they are empirical models, meaning that the incorporated observations inherently contain the signatures of solar cycle variation and geomagnetic activity. So even if F10.7 is not explicitly turned on below 110 kilometers in the model, the solar cycle inference is in the data implicitly. And also the advantage of using up MRL00 over MC90 is that it contains more and recent data with more coverage in locations and data sampling. Given these considerations and limitations, the F10.7 trend in the OH airglow temperature may not represent the actual trend. So the modeling approach, we use that two airglow models and with the MRL MC00 as a reference model, and we simulate 3 scenarios for the time period from 1960 to 2019. The 3 scenarios are for the S1, it is when F10.7 and AP index can vary, but CO2 is fixed at the level in 1960. And S2 scenario is when F10.7 AP index, they are fixed, and the CO2 variations are allowed to, CO2 are allowed to change. And S3 is when F10.7 AP index and CO2, they all vary. And we use linear regression analysis, very simple, straightforward. We just want to see what is the F10.7 trend in the temperature. Same for the AP index and also CO2. So this one shows the time series of the simulated OH temperature for the 3 scenarios. The top one is for plotting against F10.7. And the bottom one is plotted against AP index. As you can see, let's just look at S1 when F10.7 AP index can change, but there's no CO2 variations. We can see that the airglow, which is the airglow temperature, in some years it shows it follows F10.7 variations, but some other years it does not show such variations. Roughly speaking, OH temperature seems to follow the temperature, follow the F10.7 not so systematically. And for the CO2 increase, it shows that the OH temperature is going to decrease in time. And if we look at the response of OH temperatures to AP index, we can see that it shows an anti-correlation very closely. And then the next slide shows the time series of the O2 temperature. Now for the O2 temperature, we can see that it has a better correlation with the F10.7, and the CO2. The CO2 also can cause the cooling in the O2 temperature. And the O2 temperature show a very high correlation with the AP index. And similar behavior is also seen in the O1S temperature. As you can see, for the S1 or S3, it shows a moderate correlation with the F10.7, and shows a very very strong correlation with the AP index. So we did the linear analysis, the trend analysis, fitted with the AP and with the F10.7 separately, and you can see that for the AP, it shows that all this airglow temperature show a very high correlation with the AP index. You can see the coefficient of the correlation coefficient, they are very high. And the OH temperature shows shows anti-correlation. It has is proportional to -0.2 AP, and for the O2 and O1S, it shows a linear relationship. and with the O2 having a larger slope than the O1S. Now let's look at how the airglow temperature in response to the F10.7. When these are fitted with the F10.7, you can see that the OH temperature show a very a weak, moderate to weak correlation with F10.7, and its anti-correlation is negative. And for the O2, it shows a moderate correlation and has this magnitude. The slope is like 0.038, and for the green light, it has the slope of 0.0172, and it also shows a moderate to weak correlation with the F10.7. So this table shows, when we did the linear trend analysis on OH temperature, O2 temperature, and O1S temperature, and have three scenario, for each scenario. And this circle one shows the, for S3, when all three inferences are allowed to change, what are the, the slope, the trends, what are the trends, and also the coefficient, the correlation coefficient. As you can see, for the temperature, for OH temperature, it shows a weak correlation with the F10.7 and a moderate correlation with the AP. For the O2 temperature, it shows a moderate correlation with the F10.7 and high correlation with the AP index. And for the O1S, it shows a moderate to weak correlation with the F10.7 and a high correlation with the AP index. And the trend, so the trend, you can just look at the trend values. So we're going to compare the our results to some of the published results. Now for this one, this is the OH temperature. It shows the trend identified from the OH temperature shows a 4 Kelvin per 100 solar flux units, and the linear trend shows a negative this magnitude. Now for the Perminov, also use the OH temperature, it shows a larger cooling trend. And Homan et al. Shows the F10.7 roughly in this range, and also shows a negative. That when you consider the uncertainty, actually from negative to positive, but it has a trend, linear trends this magnitude. Now Holt et al. Use the mutual radar temperature, seems to have a larger cooling trend. Nazim et al. Use the OH temperature, shows a positive, actually increasing trend, linear increase in trend, and but with the F10.7, that's in the ballpark with other studies. So our modern results, using the S3 scenario, and we can see that we have the OH temperature that's showing a negative F10.7, that's rather weak, F10.7 trend, and also a weak AP index trend, and a negative 0.53 Kelvin per decade cooling trend. Now for the O2, we show our F10.7 trend is consistent in the ballpark with the other studies. And our AP index trends about 0.6 Kelvin per nanotesla. And for the O1S, we have a smaller F10.7 trend than other studies. For the AP index, it shows a 0.4 slope. And both, so you can see that all the airglow temperature, they all indicate a linear cooling trend that is due to the CO2 increase. So, here's the summary and also the key findings. Two airglow models, OHCD00 and MLT models, are used to simulate airglow temperatures of OH, A3, O2B1, and O1S for 3 scenarios from 1960 to 2019. And for the S1, we allow the F10.7 AP index to change. And for S2, we allow CO2 to change. for S3 will allow all three inferences to change. So our key findings are airglow temperatures are highly correlated with the AP index, and airglow temperatures are moderately correlated with F10.7. Airglow temperatures display a linear decreasing trend by the increase of CO2, which temperature responds to F10.7 AP index negligibly. But as we mentioned, it might have to do with the reference model that we use. So this is like, we're going to put a question mark, if we have more data, then we can, can probably like, or better reference model, then maybe this would change the picture. We don't know yet. And here's the, and also the last finding is that airglow temperatures can be affected by geomagnetic activity. So comparisons of our model simulations and the reanalysis of some of the selected observations to the CEDAR observations have been reported in another work, and that is under review. Thank you for your attention. If you have any question, you're welcome to email me. To send an email to tuh4@phdu.edu. Thank you. Bye.